Hello, everyone. Thanks a lot for coming today on this sort of, a little gray day. Super Tuesday, as I say, but it is a great day. It's a super day. Before we get started, I want to say a special thanks to Anthony Patterson and Amanda Sherman, who are on the committee for the Slovensky lecture. Anthony couldn't be here today. He is a little bit under the weather, but I did wanted to say that. And this is the second annual Donna J. Slovensky SHP Dean's Endowed Lecture. The lecture, as most of you will know, is named for our good friend, Dr. Slovensky. Donna, I know how much you love attention in front of big crowds, but would you please wave to everybody? Yay, exactly. For more than 40 years, she was a leader and an educator at UAB. And in her honor, we bring this innovative lecture series of leaders and creative thinkers, the example that she set in our school to speak to all of our campus. We have over 150 people that registered for this. In our inaugural lecture last year, and I know many of you were here last year, we had Phil Hansen, a world-renowned artist. His message was perseverance in the face of challenge. He described his journey of developing intention tremor that was devastating to an artist and how he overcame this and, if you recall, embraced the shake. He guided us in crafting a personalized art piece that he turned into a giant piece of art that hangs next to Dr. Slow's former office. So if you get the chance, go by Dr. Hart and Dr. Slow's office and you'll see that piece, because all of you that were here last year participated in that art piece. This year, we have a different kind of an artist. Today's speaker is Dr. Matt Might, the director of the Hugh Kaul Precision Medicine Institute here at UAB. Dr. Might is sculpting the way artificial intelligence is being used in precision medicine, particularly in identifying potential therapies for rare genetic disorders. He's going to show us some real-world examples of his work in that area. Plus, he will explore the future of HI, from the difficult challenges and obstacles to the important discoveries and enhancements. Without further ado, it's my pleasure to introduce you not to the AI Matt Might that you saw on all of the LCD panels from that teaser video, but the real Matt, live and in person. Please welcome Dr. Matt Might.
All right. Well, thank you so much for having me. It's genuinely an honor to be selected for this, and I am so delighted to have roughly the next hour of presentation with you, the Q&A to follow, to give you a sense of what the future, in fact, what the present actually looks like and what the future could look like. So this title slide is actually AI generated, but this wasn't my first attempt at generating a title slide. This was, and I like to share the bloopers. So as you can see, I want you to come up with this evocative UAB themed image for the School of Health Professions and tie in everything with AI, and it got halfway there. I said, you know what? Maybe don't use words. It's not your strong suit. But it's still a pretty image. Yeah, but I'm not sure what the degree MHPT is, but it gave me one. And it seems every time I speak on campus, I get another email from a lawyer saying you need to add another disclaimer to your talk. So I have 3 disclaimers today. Here's the first one. ChatGPT is not HIPAA compliant. So if it looks like I'm using ChatGPT with patient data in this, I'm not at any point doing that, and you shouldn't do it either. Moreover, ChatGPT may plagiarize. So if you're going to use it for any kind of academic writing, don't. I will talk about, or I can talk about ways in which it can help you with academic writing, but writing for you is not the best way to use it. Finally, ChatGPT may lie. Do not trust what it says. You must verify everything that comes out of it. And ChatGPT, I'm just using that because it's the one everybody knows about right now. There's lots of AI systems out there, but they all have the same kinds of vulnerabilities, including the one that we built here at UAB, which I'm going to talk about. And I guess my final disclaimer is that I'm a computer scientist, and that there is, in fact, what appears to be medical advice in this talk. But don't take it. I'm not qualified to give any of it. In fact, not only is there medical advice in this talk, but literally all of it has been generated by a computer. So please bear that in mind and consult a qualified physician. So just to give you a sense of where I've come from, my old life actually was a lot of things like cyber warfare and cybersecurity. So when I was really just a pure professor in computer science, I was out at the University of Utah. This was my probably 60% of what I did was lots of work for DARPA, DoD, folks like that, in using things like AI for cybersecurity. I also did a lot of supercomputing, and including a lot of supercomputing for climate solutions. But my core research area was actually what I would describe as what it means to use language as the interface between humans and machines. And I think since we all know about things like ChatGPT now, this is obviously an area that's gotten quite exciting over the past year. But I had a full pivot to precision medicine, which is what ultimately brought me to UAB. And I'll give you the abbreviated version in a little bit of my life story. This isn't a talk about my life story, but it'll help set the context for how I ended up in this weird nexus of health and AI. And if you're wondering why it is me, the sneak preview is actually about my son. So this is my son, Bertrand, back when he was about 1.5 years. And he is the one that pushed me into precision medicine. So I'm going to start today with a claim, or really a series of claims, including some claims I've never made before. But the first claim is that when we look back on the history of health professions, medical sciences, you name it, for the 21st century, I think we're going to see that data was in many ways the greatest drug development. I mean, data used interventionally to improve the health of human beings. Moreover, I claim that if you want a very quick definition of what precision medicine is, it's really the field of medicine, which cuts across all the others, in which we do deliver data as a drug. Now, to do this, given the amount of data we have out there, you really have to invoke computation. There's so much data about patients and outside of patients that you can't really do this without using a computer. And I further assert that there's a specific kind of computation that is especially important in precision medicine, and that is artificial intelligence. So when I came here about 7 years ago, it was essentially the first strategic bet I placed, that we needed to invest very heavily in artificial intelligence, biomedically literate artificial intelligence, if we were ever going to see precision medicine become real. And you're going to see some of the fruits of that investment in just a moment. And so I would say that in some sense, if you take medicine and you enhance it with artificial intelligence, you can't help but get precision medicine. And I'll further conjecture now that if you want to take health professions and you develop the precision version of them, I think what you probably need to do, and this is a discussion we can have, is augment them with this newer kind of artificial intelligence. So those are my claims for today. I really want to get 3 major questions answered through the course of this lecture. I do want to explain what precision medicine is, because it sets the stage for my interaction with AI. But then I want to move beyond that. I want to start talking about what AI is more generally. And I'll talk about 2 different kinds of AI, in fact. And mostly what I want to do is give you all a sense of what's already possible and what's about to be possible. I want you to leave here with a sense of the building blocks. What are the fundamental technologies that are now available or shortly going to be available that you could assemble together to create any kind of AI platform or precision health platform. So I'll begin with a quick overview of what precision medicine is. If you've never engaged with the Institute before, you'll have a very good sense of what we can do after this and why it is we ended up doing so much in AI. So the field as a whole is relatively young. It really began with this report by the National Academies back in 2011. And if you look at the glossary, there's this essay-length definition where they're trying to distinguish it from personalized medicine and end up saying it's the same thing as personalized medicine. And it really all just boils down to this. They say that precision medicine is what you get if you are tailoring treatment to the individual characteristics of a patient. And in fact, if you read this report, it's quite long, the word data, as in patient data, appears on essentially every page. So it is all about data. And so for my working definition of precision medicine, I just say that precision medicine is what you get when you're trying to optimize health with data. And what that means is I think of it as a process, where we're trying to map a patient over to the best possible set of treatments for them. And in this process, we really do begin with their data. And there's lots of data you can get around patients. So I think the piece of data that kickstarted precision medicine, the one that made computation necessary in many respects, was the human genome. The sudden clinical accessibility of the human genome required doing medicine differently. To essentially have this blueprint for each patient necessitated engaging with computation in order to start solving or answering the question of what is the best possible treatment for this patient given their genetics. But there's always been data sitting around patients that you can leverage. In fact, if you look at the electronic medical record, I would say we still haven't fully saturated what you can do with the electronic health record for optimizing patient health. And then there's all the data outside the patient, sitting in textbooks, biomedical data sets, papers. All of this should be part of this optimization problem. So I'll betray my background in engineering and say this is how I think of it, truly as an optimization problem, where in modern healthcare, what we're trying to do is modulate things like treatment and lifestyle in order to arrive at the optimal combination for health. This, in some sense, is the problem. I think what would really help now, to get away from the abstract, is just show you two stories. Just literally tell you about what it's been like in the Precision Medicine Institute using AI to help patients. And so here at UAB, we're very lucky. We actually have this institute that's focused on this. And our mission, as I define it, is to do science in the service of patients. So there are times when you run out of standard of care, you run out of clinical care, and that's really where we step in. Because when that happens, science is what becomes medicine. And what we try to do is provide the roadmap for patients and say, well, this is what you can still do in the context of science. I have to give credit to the amazing medical leadership team we have. We have Madeline Eckenrode as our medical director, Tony Farguson, who's also the chief medical officer at Children's, as our deputy medical director, and then our incredible program coordinator, Alexandra. She's actually sitting up there. So if you feel like you or anybody you know needs precision medicine, she's the person to talk to right after this lecture, and she'll help you get referred into our program. And there's also a very large team of undergraduates that helps with this as well, that really makes all of this possible. And in many ways, what these undergraduates are doing is serving as the care traffic controllers. And they're interfacing with the science and scientists, they're interfacing with clinicians, they're interfacing with patients, and they're interfacing with computational tools, many of which are in fact driven by AI, and really doing a lot of the heavy lifting so that they can put together research reports verified by the medical directors that then go back out to the treating physicians for the patients that we've engaged with. So I always like to give credit to them because it really wouldn't be possible without them. And the first story I'll give you is Kelsey's story. So this is, what I like about it actually is it doesn't involve, a lot of, or any genomics. There's no genome in the story. And yet AI is incredibly helpful for this young woman. So when Kelsey's parents reached out, she was about 19 years old. And unfortunately, and I should say all this is shared with her permission, suffering from intractable cyclic vomiting syndrome. So she was essentially frequently in induced coma in the hospital, and despite being about 5'4", she was 75 pounds, suffering dozens of vomiting episodes per day. And of course, her medical team says what we always hear: we've tried everything. And if there is an admission criteria for getting into our research program, that's pretty much it. You have to say you've run out of everything else and you've tried everything. Now, in their case, everything was about 25 things. It's a lot. That's a pretty exhaustive search. So we actually went ahead and read everything. And by everything, what I really mean is 30 million published papers. And this is where those undergraduates are so indispensable. No, I'm just kidding. It wasn't the undergrads. So of those 30 million published papers, there's about 64,000 on nausea. And about 4,000 talk about treating nausea. But between those 4,000 papers on treatment, there's only 347 distinct proposed treatments for it. And this gives you a sense of the two definitions of everything. There's everything that you learn about in med school, everything you learn about as a physician or clinician, and then there's everything that's actually out there. And I can even show you the distinction between these two as a graph. So what you can do with is you could take every proposed treatment for something, and you could rank it by the number of publications that talk about it. And you get this kind of log scale plot, or this log curve every single time. And right up at the top, you'll find something like for nausea, you'll find Zofran. Not a surprise. There's 169 papers that talk about using Zofran for nausea. But if you go way down, deep into the tail, you get to stuff like nasally inhaled isopropyl alcohol, with 3 papers that discuss it and its effectiveness as a treatment. And so if you zoom back out, the everything that people talk about is what we call the known. It's the stuff that everybody learns about in their training. Then there's that long tail. It's the stuff that we as a species know because somebody published something on it, but no one remembers anymore because no one's read it. And so when I say we read everything, obviously it's not the undergrads. It really was artificial intelligence. And so just to give you a sense of the technology we started off with 7 years ago, like if ChatGPT, if that's Homo sapiens, we use like the Homo erectus version of natural language processing and artificial intelligence. But the thing is, that was good enough. It's remarkably good enough, in fact, to find and parse all of the literature in such a way that we could identify novel treatment options, or at least treatment options not yet considered. So we sent those 3 papers over to the clinical team, and they said, hey, never heard of this, let's try it. And it worked. So she was able to arrest essentially every episode of nausea after that day. Fast forward to 8 months, we got an email from her mother. She said not only is she no longer vomiting, but she's up to 125 pounds, and her high school sweetheart proposed, and they got married. So he had been visiting her every day in the hospital, and shortly after this, they moved to California for his job. So the question is, can we do more? And of course, the answer is yes. And the way we've done that is through a fairly sophisticated AI called Medicannon. So this is something we built in-house here at UAB, courtesy of some generous funding from NCATS at NIH as part of their biomedical data translator program. And what this AI is it is a fusion of logical reasoning and all of the biomedical knowledge that we can get our hands on. So biomedical knowledge that's been absorbed for 7 years now. So we have far more than just the literature. The total number of databases that have been absorbed into Medicannon is north of 150. So there's a lot of data sitting inside this thing. And here's how I would describe what it really is. It is a fusion. It's what you get when you take old school logic and combine it with high-speed automated reasoning to achieve superhuman-like deduction with clinical insight. At least that's always been our goal to do this. And I can show you what a brain looks like for an AI like this. And I'll show you what other AI brains look like in a moment too. But if you sort of look under the hood and see inside, what you would find is a large number of circles. And each of these circles inside this AI brain is a noun. It's a concept. It's a thing from biomedical sciences or clinical practice. So there's genes, there's drugs, there's diseases, there's symptoms, mechanisms, pathways, all the things that make up biomedicine. And between those circles, you would find arrows. And these arrows are labeled with verbs. So verbs like inhibits or activates. And so you can actually encode sentences, knowledge, into the brain of this thing by drawing arrows, subject, verb, object. So that's what's inside the brain of an AI like Medicannon. And the more databases it absorbs, the more circles go into its brain, the more arrows that get drawn. The important thing, just as for example, if you wanted to encode the sentence, Prevacid inhibits N-gaze into the brain of this thing, you can do that by just, again, drawing an arrow from Prevacid to N-gaze and writing inhibits on it. The key thing here is that once you have all of this knowledge in there, you can start looking for the hidden connections, hidden by logic, that is. So if, for example, you know that concept blue, whatever it is, increases concept red, and concept red decreases concept green, you can infer logically that by increasing a decreaser, ultimately blue should decrease green. That's a logical inference. So that dotted line may not exist anywhere in the literature, it may not exist in any databases, but you can infer that it should be there based on what you already know. And that can be quite powerful sometimes when you're looking for novel or hidden ways to treat patients. So, and at the end of the day, the brain for an AI like this, it's a soup of circles and arrows encoding all of that knowledge. So you can ask a tool like this, what may be a treatment for this disease over here? And it can think creatively, logically, abductively, deductively, inductively, over that knowledge graph, looking for ways to do that. And the key advantage here, by the way, is that it will always explain how it came up with an answer. It'll say, well, I think this because, and then it'll give you a logical argument. Or you could use it how we use it most of the time, where we know specifically in the context of some patient, this is the target we need to hit, this is the direction it needs to go, up or down, and tell us drugs that might do that. So as an example of that, we have MapK8IP3, it's our second AI story. And in this case, it was a 5-year-old boy that came to our attention through the Undiagnosed Diseases Network. The Institute is actually part of the Coordinating Center for the Undiagnosed Diseases Network. It's a national network of clinical sites that see essentially the toughest diagnostic cases in the entire country. So when this 5-year-old boy reached out, he couldn't walk or stand, so totally non-ambulatory. And ultimately, it was determined that his MapK8IP3 gene was underactive, which means the question for Medicannon was, how do you activate it? And what it came back with, in like the blink of an eye, was high-dose retinoids. So I mean, it didn't just come back with that, it came back with answers patched together from the literature that we could send to a clinical team and say, hey, look, have you seen these papers? Do you get a sense of what they imply? And they got it right away. They said, okay, well, we can put them on essentially the maximum safe dose and see what might happen here. So not much happened right away. And that's often the case when you're dealing with a developmental disorder. In these cases, you might have to wait a while to see something happen, but we did eventually see something happen. So his mom emailed us this video about 6 months later. And she said, look at this. He is actually taking steps. So basic steps, but definitely steps. And standing. So again, some basic steps. And that's a pretty big difference from not being able to stand or walk. And then we got another video about a year later, so 18 months into this. And this is that video. And it's almost night and day, even from the prior video, and even more striking from the descriptions we were getting from 18 months prior. And you'll see in a second, he can even bend down and pick himself up. Then the thing you have to realize
you're doing great.
Is that this is not just medication. This is also a parent that is spending more or less all day, every day in physical and occupational therapy with her child. Trying to maximize whatever potential there is or whatever potential gets unlocked.
That was
So there you go. 18 months in. And I do want to just mention that, while we do a lot of computational stuff, there is still value in the old-fashioned wet biology too. So as my colleague Ethan Perlstein calls it, the organic intelligence. And so we actually have a center here, you might not be aware of this, at UAB called CPAM. So CPAM has a lot of infrastructure to study rare diseases in the context of animal modeling. And so Brad Yoder and I, we run this as co-directors, along with a very large team. And what we can do is we can take the molecular characteristics of a patient and we can actually put that into a precision disease model with genomic engineering. And what this allows us to do is essentially build a precision disease avatar of a patient. And so what's interesting is we've actually encountered other MapK8IP3 patients over time. And it even more interesting is that there's appear to be multiple disorders within the same gene. In some cases it's underactive, some cases it seems to be perhaps a toxic change in function. And so for some of these other patients, to find what helps them, we actually have to model them and use a zebrafish, as it were, as a computer. And so our amazing faculty member, Cami Crowder, has done exactly this for one of those patients. And what she discovered by looking at some of the suggestions from Medicannon, by actually testing them on zebrafish, is that amantadine seemed to rescue the phenotype for that patient's fish. And as even said recently, that amantadine has given that patient really remarkable gains in both cognitive development and physical development for that. So if this were all about precision medicine, I'd give you, far more stories just like these. I would tell you about how we used AI to find and ultimately get into a clinical trial of ketamine for a rare genetically driven autism that was actually successful in the end. Or about the use of lisdexamfetamine for an ultra-rare cataplexy driven by overactivity in a potassium channel, or about the use of guanfacine for this synaptopathy. But I'll tell you just one more story to give you some additional context. I'll come back to it at the end, which is actually my own story and why I do any of this. So back to Bertrand. And turns out that Bertrand was the first case ever discovered of an ultra-rare genetic disorder. This is back in 2012. As a matter of fact, he was the first human being diagnosed using exome sequencing. So the clinical genome, genome sequencing was the first to do it. He was the first exome way back then in a pilot study of this at Duke University. And from that, there was an article written up in the New Yorker describing what that was like. The discovery of a disease, the founding of what became a patient community. And then my life started shifting from computer science because I ended up with a secondary appointment in the College of Pharmacy and pharmaceutical chemistry. I helped launch a natural history study at NIH into this disease. I ended up serving initially as a consultant for the Undiagnosed Diseases Network, and then things kind of snowballed further from there. So based on what I was learning at the time in pharmaceutical chemistry and from the natural history study, I actually hypothesized the first meaningful treatment for the disorder, which is now used by virtually every patient. I won't go into what that was or how it worked. I'll talk about some others in a moment. But that also led to founding a startup company designed to do the same thing over and over again in the somewhat narrow context of ion channel-driven epilepsies. And in fact, it worked. It was so successful that it was acquired a few years after it started in 2018. The involvement with the Undiagnosed Diseases Network led to what I would say is the full sort of formal pivot into academic medicine. I ended up on the faculty at the Harvard Med School, and then came really the opportunity of a lifetime. So I ended up getting called to the White House to meet with President Obama before the launch of the Precision Medicine Initiative. And what he said was, hey, I read your article in the New Yorker, and I want to launch this national program around precision medicine. Would you be willing to help? I said, yes. So I ended up working at the White House for 3 years after that. And what I helped do there was architect this precision medicine initiative, which has since transformed into the All of Us program, of which UAB is one of the largest clinical sites in the country. After that, I was actually offered tenure at Harvard, and I did what any reasonable person would do with an offer like that. I said, heck no, I'm going to Alabama. And that's because I got truly, I think what was the actual opportunity of a lifetime was to come here to UAB with the full support of the university. In fact, beyond the university, and to build this institute from scratch in such a way that I knew we would be able to help patients. And that ultimately is what's most important to me, is making a difference for patients. And you might be wondering, has Medicannon made a difference for Engelai 1? And it has, So I actually ran the query almost as soon as the tool was built. I said, can you think of ways that might treat my son's disorder? And it said, yes, I found something. I think what you need is broccoli. More specifically, it said there's a component within broccoli, it's sulforaphane, and it said you need, broccoli might actually modulate one of these compensatory pathways in the disease. And then it said, by the way, what you really need is about 60 pounds of broccoli per day. And fortunately, you can buy condensed, distilled sulforaphane pills that, so you don't have to take 60 pounds. It's like, look, Bertrand was never going to take even an ounce of broccoli, but he would take the pills. So over the course of his life, all of these things started to really make a difference for him. And what I tell folks is that by the metric that really matters in anything in life or medicine or whatever else you want to do, the real metric is the one you measure in smiles per hour, and this is the metric where Bertrand really excelled. And in fact, through a combination of interventions, continued to progress developmentally to the point where eventually he was even using an eye gaze computer. And so he was able to say things like, hello, like, Matt is my dad when I would come home. And again, full credit to all of the occupational therapists and speech therapists that work with him over time to make something like this possible. So I'll pivot now towards the main course for this talk. But before I do that, I just want to say we actually need your help. So we actually have built a public interface to that tool I talked about, courtesy of some funding from NCATS. In fact, it's an interface to several tools just like it. So please use it and tell us if it works for you. And if it doesn't, we actually have funding. We'd like to interview you and figure out why it doesn't work for you and how we can make it better. So that there's a lot beyond AI and precision medicine too. We're doing a lot, and about to do a lot more in the context of precision oncology and antisense oligonucleotides, what I'd like to think of as programmable therapeutics. But that's not the point of this talk. What I really want to do is now give you a sense of what is coming with AI. And so we're entering a new era, and I would say it's the era of generative artificial intelligence in health. And by the way, this image was generated by a generative artificial intelligence. And the way you can tell is by looking at the hands. In fact, virtually every image in this talk was generated by an AI of some sort. And I used to tell folks, and by used to I mean like last week, I used to tell folks this. So you could always tell it's AI generated by looking at the hands. Well, guess what? A new model just came out, and this is now the image you get. And by the way, the hands are just fine. So I guess we'll have to look for something else now. And if you want to know what generative AI is versus the AI I talked about with Medicannon, it is essentially a human with, or it's a computer with human level creativity. That's the way I would put it. And the best example of this is obviously ChatGPT. There's a lot of others that are out there. And the cool part about a generative AI is you can ask it, what are you? What is generative AI? And you can say, oh, by the way, explain it like you're a high school student. And it will do that. It will write you a paragraph that says, oh, hey, this is what generative AI is. And it basically is saying, I'm something I learned from examples. If you give me lots of examples, I can try to create new examples based on what I've seen. We've got our own version. It works very similar in a lot of ways. It's called Medicannon GPT. And you can ask it, just like you would ChatGPT, say, hey, give me a 3-sentence summary. It will do exactly that. It has some distinct advantages I'll get into over ChatGPT. A lot of what I'm talking about can be done with ChatGPT. If it needs Medicannon GPT, I'll try to mention that. But now I want to get into applications. And what I've tried to do is look at the different disciplines within the School of Health Professions and pick out ways in which I think AI can make a difference. But really what I want to do here is give you the building blocks. I mean, you know health professions better than I do. So when I want you to think about how to assemble these building blocks to improve what you do. But one area is clinical diagnostics. And we've actually got a collaboration ongoing now in the context of infectious disease. This is with Dave Kimberlin. He does pediatric infectious disease at Children's. And he has sold me on the idea of building a sort of a hyper-focused, specialized AI for diagnostics in pediatric infectious disease. And the way we're going to do that is by taking what they call their Bible, the Red Book. It's a full description of essentially every known infectious disease. And we're going to convert that into a specialist AI. That book is like thousands of pages long. But what we essentially want to do is turn that book into something you can have a conversation with. You can say, hey, I've got a patient with these symptoms. Tell me in ranked order, what do you think this could actually be? And go ahead and cite the original sources in the Red Book itself. So for example, you can give it a patient profile. Here's a de-identified patient profile. And then it can spit back and say, well, based on what you've said to me, here's what I think it could be. And here's why I think it could be that. And its first guess is in fact correct in this case. Or you could analyze EHR data. So let me show you something that I'm building in the context of a new program we've applied for funding for. I think there's a good chance we'll get it. One component of that is to actually use your phone to absorb all your health records and then pass those off to an AI. So we've already built this app. This is an app that can pull your health records straight out of the UAB medical system, but also from almost any health system in the country. It's using some new open standards. So here's an example. A sample medical record actually pulled onto an iPhone. The full record itself, that's in a format that could be sent off to an AI for analysis. But a lot of the data that's out there when it comes to working with patients is somewhat messy. It's in things like patient journals or patient diaries, and it's highly unstructured. And this is where some of these newer artificial intelligence modalities really shine, because they can handle it. They can handle very messy, very unstructured data in the way that you or I could. They can just do it a lot faster. So here's an example of the output of an analysis of I think it's about a 5-year journal of a patient with Meniere's disease. And in seconds, it had analyzed the entirety. And this is all basically a Word doc. And this patient is saying, today, here's what happened. Here's what I did. Here's what I ate. No consistency, or at least very little consistency. And it was able to say, well, it looks like here are some dietary triggers. Here's some, things I'm noticing about the weather that seem to influence. And all of that is coming from, unstructured data at the end of the day. And so this is for this, you have to use Medicannon GPT because the amount of data is bigger than what a tool like ChatGPT can handle currently. You can also use these things to do things like clinical coding. So for example, this is something we're actually doing now as part of the coordinating center for the Undiagnosed Diseases Network. And in its next incarnation, we're moving into phase 3 of this whole initiative. What we want to do is actually, in some sense, accept everybody and have an AI service tier that will continuously surveil for possible diagnoses once you've applied and once you've entered your information, but also something that can decide, should this case be escalated to higher service tiers, where there's telehealth or an in-depth on-site visit, or does this patient need to go directly to research? Is there something we can do in a research context that could help them in their diagnostic odyssey? As part of this, what we're doing is we're taking highly unstructured inputs. In this case, it's a referral letter. It's a de-identified referral letter written by a physician saying, this is why I think my patient should be accepted to the UDN, and converting all of these into uniform structured summaries that look identical in every case, or at least identical in the sections. Part of these summaries are actually a short encoding of the phenotype of the applicant. In this case, we're using a vocabulary called the human phenotyping ontology, very common in rare disease. And what we're finding is that we can do this coding in a matter of seconds, whereas it takes humans hours and hours, if not days of their time, to do these encodings correctly. And in fact, we're finding now that even if you give the human experts access to clinical records, we still, off just the referral letter, oftentimes pick much better codes than the human experts. And the general algorithm we've developed for doing this seems portable to other coding methodologies. So ICD-10 codes, CPT codes, all of them seem to be in scope for this approach. And in every case, it looks like we can do better than the human coders, or provide a secondary backup to the human coders to say, hey, you might have missed this code here, or I think this would be a better justification for this code over here. So now what I'd like to do is actually shift into an even deeper dive and give you a better sense of what these AIs, these newer generative AIs actually are. And the best way I can describe it, and this is it's not really a lie, this is the truth. They are, to a large extent, simulated brains. That's what's sitting underneath a lot of these newer technologies. So in computer science, the term would be an artificial neural network. And so to understand what they are, you actually need to go back to biology. You need to know what a neuron is. And in this case, what we really need to do is not what don't need to know what a neuron is. We need to know what it does, how it behaves. And from a computer scientist perspective, a neuron is just a transducer. It takes input signals, it mixes them together, and you get an output signal. And what's even cooler is that since about the 1940s, we've had a very simple but reasonably accurate mathematical model for how this happens. So it turns out you can model a neuron mathematically with a little bit of multiplication, a little bit of addition, and like a very, very tiny pinch of calculus. And that's really all you need to do this. And then what you can do is you can connect these things together. And in fact, you can just make deeper and deeper and deeper neural networks and wider and wider and wider neural networks. And what starts to happen over time is that as these things get bigger, much as is the case with human brains, they get smarter and smarter and smarter. And what's interesting is that when this technology was discovered and the first neural networks were truly implemented in computers was back in the 50s, they did some pretty cool stuff right out of the gate, but they didn't get a whole lot smarter. They were getting smarter and smarter, but people said, it's never going to work. And so the idea was kind of dropped up until the early 2000s, when some researchers said, you know what? Computers are a lot faster now. We have way more data. What happens if you make these things really big? Oh my gosh, that's all it took. You just had to take the idea from the 50s and pass it massive amounts of data with massive amounts of computation, and suddenly amazing things started to happen. So what else can these things do? And this is now to give you a sense of these building blocks. Well, they can generate images, as you've seen. So I had to give a talk at NIH about CPAM one time, and I was like, I want an inspirational title slide where we have a superhero version, like the mutant power version of each of our animals. And so I had it generate that, which is interesting. It did a really good job with everything but the fish. I guess it's just hard to make fish into superheroes, with all apologies to Aquaman. But that's not, again, this is not the first image generated. This is the first image generated. It actually fused all 5 organisms into one organism, which I think is even cooler and more creative than what it did ultimately. And then you can just say, well, I want to see a photo of a desert canyon, on a starry night. Or you can do what I did when I was taking my kids on a trip to Alaska last summer. I could use it to give them a sense of what it was going to be like there. So we were going to do some dog sledding, but they love pugs. And so I said, well, this is what it might look like. But again, this is the second image it generated. The first one was actually a sled of pugs pulling a sled of pugs, which, to be honest, is probably much more accurate. It's what actual pugs would do. And then we went salmon fishing with bears, and this is what it thought that might look like. And actually, it was pretty close to that, or like this. And then my son said, well, what about a sentient cabbage wearing army gear? And I said, this is what that would look like. So, it's just ridiculous at this point how much human creativity seems to be captured within these models. And they can actually generate what appear to be relatively accurate synthetic medical images, which could be useful for training. And the other direction also works. You can take an image and say, what is this? So this is the one that I think is the freakiest, and actually has implications for later on. It says, I was at Chick-fil-A. I took a picture of my Chick-fil-A sandwich, and the sentence in the middle is the one that really gets me. It says, the person is holding the sandwich in their right hand and is looking at it with anticipation, which of course I was, but how did it know that? It's because, well, any reasonable person looking at that sandwich would be looking at it with anticipation. And it gets to something deeper about what these neural networks have learned. To get smarter and smarter and more accurate at what they do, they have had to develop entirely on their own a theory of mind, and that's what they've done. They have they've absorbed the ability to intuit the mental states of others being us. And so, for example, if you give them a transcript and say, how do you think this character is feeling at the end of the transcript? They can tell you what the likely mental state of that character is. Of course, image-based AI diagnosis has been around for a while. So in rare genetic disease, you can take a picture and you can use images of a face in some cases to try to get an accurate diagnosis or potential diagnosis for a patient. And you can, but you shouldn't, upload actual medical images to ChatGPT and say, what do you think? Now, you shouldn't do this because, one, again, you can't put PHI in ChatGPT. And furthermore, they say right up front, you shouldn't do this because we're not guaranteeing it's going to get it right. The amazing thing is it gets it right a lot. But again, you shouldn't do it. You can also manipulate images. So this is Andy. He's the number 2 at the Precision Medicine Institute. And I just want to say, okay, well, I want to see Andy, but I want to see what Andy would look like if he were Thor. And that's Andy as Thor. Or as you saw from the trailer video I made, you can do it with video. And it took me about a half a day to put that together. And I needed some practice in manipulating video. So this is actually the first synthetic video I made using AI, I actually just put my face on Biden. And sure enough, look at that.
And that's because the former president has said a dangerous and shocking.
Anyway, the real power in some of this, though, is actually something boring. You can use all this super high-powered computer vision to read PDFs. In fact, it's really, really good at this. So this enables, I think, some of the most interesting applications in healthcare. So here is a de-identified genetics report. And here is the result of a computer vision AI, generative AI, telling me in a structured fashion what the most important parts of that report are. The gene, the variant, all of this stuff. It just pulls it right out. And then you can use this to kickstart a virtual genetic counseling session. So this is Medicannon GPT taking that PDF and starting a genetic counseling session based on that. And what's cool is you can ask it questions. You can say, hey, I don't know what a VUS is. Can you explain these things in lay terms? And it can. It can shift registers. In fact, not only can it explain these things in lay terms, you can say, well, just explain it in lay Spanish, and it will. It will translate on the fly. So generative AI can write code. And so, for example, if you have a bioinformatics problem, you can say, hey, I need help solving this bioinformatics problem. And it will just step you through it. It'll say, like, okay, here's the code I think you're going to need. And if you get an error message, tell me what it is. I'll help you fix it. And so you can have this kind of interaction with it as you write code. But because it can write code, that also means it can analyze data. And I think this is one of the most powerful features of generative AI. So I'll tell you another true story from Alaska, where it's actually the first time I ever used generative AI to write code. So at 11 o'clock at night, while I'm sitting on the coast, this goes off on everybody's phones in the RV park. Tsunami warning. There's been an earthquake off the coast. And so I looked at tsunami.gov, and we're in the middle of that red blob. I went, oh, well, this is really bad. What are we supposed to do? And my dad, who's with us, he's a sailor. He said, by the way, there's this whole network of ocean buoys out there run by the government, and you can actually access their data feeds in real time. I said, oh, well, let me do that. So I started picking out the buoys that were going to be hit by the tsunami, because it looked to me roughly an hour-ish out from it, and the first points of impact for the buoys were going to be about half an hour-ish away. So I started grabbing those buoys' data. This is the real-time feed coming from those buoys. And I said, I need you to write a program that will analyze this buoy data in real time to look for statistically aberrant wave heights that would indicate the presence of a tsunami. That's what I did, and it did that. And it started plotting the wave heights in real time from these buoys. This was happening within 10 minutes of getting that tsunami alert. That's how fast all this was happening. And then watching as the first buoys should be getting hit, it said, you know what, doesn't seem to be much to worry about right here. Now, if you aggregate all the data from across all the buoys the next day, you do find that there was in fact a tsunami. It was just 6 inches high. So roughly within the realm of statistical noise for any one buoy. But you can do this with health data. So for example, if you have this is all synthetic epidemiological data, you can say, hey, here's a bunch of data, find me some clusters in it. And if you do that, it'll start doing so. What's cool is you'll notice that if you read this transcript in full, it actually makes a mistake in the middle, realizes it made a mistake, and fixes itself in the process. So it makes a mistake, it fixes it, figures out roughly how many clusters there might be, and then actually starts generating graphics showing what these clusters look like, and then describing them textually to say, here are the clusters that I identified in this data. And then I wondered, could it help in something like nutrition? As it turns out, I think there's a lot of ways it could potentially do this, but here's one I think is particularly cool. So one problem, for me, and I suspect the same is true for a lot of folks in nutrition sciences, is it can be really hard to interpret the literature, because you get so much conflicting information back and forth sometimes. You can use AI to do an on-the-fly meta-analysis for a given question. So for example, there's this tool, consensus.app, and what it can do is essentially do that on-the-fly meta-analysis for you. And I asked it, does whey protein increase muscle mass from exercise? It runs out there, it starts pulling papers, and then it starts summarizing the results. And here it's saying, well, roughly 2/3 say yes. About 1/4 says maybe, another 1/4 says no. And so the balance of evidence seems to be in favor of whey protein helping in this case. So what else can it do? Well, something else a lot of folks don't know about is the way it can do really almost flawless. So a lot of people think about Siri or Alexa when it comes to transcription, which is awful. There's newer models, which any day now I suspect will show up on our phones, that are much better at this. But one you can already use for yourself is Whisper. So Whisper is open source. Anybody can use it for free. And what I like to use it for is summarizing meetings. So we had a 3-hour external advisory board meeting for CPAM, and it listened to and generated a flawless transcript for that meeting in 5 minutes. So a 3-hour meeting, transcript in 5 minutes. And then, because the transcript was so long, it had to go to Medicannon GPT, but it summarized the whole transcript in 10 seconds and gave us a quick high-level summary of what had happened at that meeting, what the action items were, and things like that. I think I've shown you some of the key building blocks, and now we can think about how they might get assembled into an AI-powered hospital and the implications this could have for administrators. So, what you could do, there's nothing technologically stopping us from doing this right now. There's certainly issues we have to work around with policy and regulation, but you could generate a transcript of every conversation happening between patients and clinicians in a hospital. That technology exists right now. So you can take that transcript and you can convert it, for example, into a structured summary automatically. You could turn it into a SOAP note. You could turn it into a differential diagnosis. You could turn it into follow-up, one for the physician, one for the patient. Or, this is one I think where it starts to get very interesting, you can even score the bedside manner of the clinician. Again, if you go back to that Chick-fil-A example, where it knew my state of mind, this is what makes something like this even remotely conceivable. One of the axes on which it's scoring bedside manner is whether or not the physician displayed empathy, whether or not the physician engaged in active listening. So it is having to intuit states of mind from the transcript to do something like this. And that's actually pretty important. If you look at the crisis of burnout in healthcare, one of the early warning signs is a drop in empathy. And so maybe it's possible now at this point to proactively monitor empathy and in real time see, is this clinician's empathy dropping? And if it is, maybe we need to do something about that. Now, there are obviously privacy concerns to work out here, but they are something we could work out. So it is possible to run the system entirely locally. A physician could run it literally for only themselves, so that only they have access to the data, and they could do this analysis on themselves if they want, transmit the high-level results. So that's possible today. I could run that on this laptop right here. But even cooler is you can address another pain point, which is the fact that literally everyone hates electronic health records. So physicians hate all the time they have to spend working with them, and because these things can write code, they can write code that interacts with the health system or with the medical record and says, hey, are these the orders that you want to put in as a result of this? Just check yes for the ones that you actually wanted. Again, all based on the fact that it could listen to and transcribe a conversation. I also wonder, can AI help with mental health? And I can tell you about my own experiments in this space. So there are already some interesting applications out there for your phone. There's one called Bloom that uses AI to do cognitive behavioral therapy. I built my own virtual therapist within Medicannon GPT, and I've trained it to do things like cognitive behavioral therapy, mindfulness, and then give you anecdotes from Stoic philosophy, because that's the kind of therapy I like. And for example, you could say, hey, I'm feeling stressed at work. I feel like I've been getting more than I can handle. I have too many patients. I can't do my job well. And they'll start breaking down. Okay, well, this is why I think you're feeling this way. And here's the things that you might be able to do for that based on the kinds of interventions you've said you appreciate. So this kind of thing is already possible. And I'm thinking, well, if that's possible, why not have, say, a virtual nutrition coach? There's apps like Noom, which seem to be very effective in helping patients with things like nutrition and weight loss. Why not scale that up further by having an AI coach with you at all times? I've wondered, based on my experiences with my son, how AI could impact occupational therapy. And one of the things I realize is about to happen here is I think through AI, we're going to see an explosion in interesting assistive technologies. So I myself have been playing around with this Apple Vision Pro, And it really enables, I think we're early on in this space, enabling or playing around with what it can do to reinterpret your environment for you. And if you have an AI sitting inside of that thing, watching the environment in real time with you, I think the possibilities are really endless. I did actually also get Medicannon GPT to run in it, but it just runs as a window floating in space. It's not that interesting yet. But maybe someday it'll be a virtual person you can talk to. And then in terms of things like physical therapy, one easy thing I think it could do right now, and this is an area where I think collaborating with experts would make this significantly better, is a tailored exercise plan. So for example, if you were to give it the profile of a patient, including things like their goals, their limitations, and the equipment available to them, say at home, it can generate a plan that says, I think this plan might work for you. Now, whether or not this is a good plan, that's up to human judgment at that point, but it is a plan that it can generate. So maybe what it helps with is, coming up, generating a plan quickly so that you can double check it, edit it as necessary, and move on. So to close things out, I want to start getting into some of the nuance. So when you might want to use a tool like the one we built versus the stuff that's commercially available. So obviously privacy is an important one. If you value the information, do not use ChatGPT. Nothing you put into it will be private. All of it will end up in the training data for the next version. Medicannon GPT has privacy guarantees, on the other hand. It will be HIPAA compliant, so I've engineered it and constructed it, and I attest to its HIPAA compliance, but UAB, HSIS has not yet certified that, so until they do that, don't put health data in it either. More importantly, you can handle about 300 pages of text at a time with Medicannon GPT. It's closer to about 16 or so pages of text with a tool like ChatGPT. So that 16 is a lot, but there are certainly times we need to go way beyond that. The next version of Medicannon GPT is probably, if I had to guess now, probably closing in on 500 pages of text that we can handle at one time. So these limits are getting very big, very fast. And more importantly, it can phone a friend. It can call the old Medicannon, which has billions of curated biomedical facts inside of it, and say, hey, is this true? Do you actually believe that? Can you cite a source for me for this information? And there are some pitfalls to be aware of. So it is possible that these things will plagiarize. They might actually replicate text that's out there. They don't often do it, but it is possible for them to do it. And so you do have to be careful. They can make stuff up, so they can generate things that look really convincing that are false. And so, for example, I didn't, because they don't do it all that often, I have to pick on one of the dumb ones, which is Google's Bard, which I guess they've since replaced. If you ask it for a list of potential inhibitors for this gene right here, it will happily give you a list of potential inhibitors. In fact, even point out its role in things like cancer biology and whatnot, except for the fact that this gene doesn't exist at all. But that's a very convincing answer, you have to admit. So the solution here is to actually merge the old and the new approaches to AI, something I was just alluding to, that we need more than just the artificial neural networks. We need them to actually call out and interact with these old knowledge bases, and old as of like a year ago. So this was state of the art a year ago, and now I think we realize we can't throw this out. We can't do everything with neural networks. We actually have to mix the two together. So, what we're really talking about is using the old AIs, which are called symbolic AIs, to do the real-time fact-checking for the newer AIs, which in turn will allow richer knowledge extraction of the data sets that we analyze for these AI, for the symbolic AIs. There's other advantages too. Sometimes generative AIs, if the information inside that you're asking for is low frequency, meaning it's not repeated a lot out there, they miss it when you ask them for it. But that never happens if you give them the ability to query other data sets and tools, which is what happens if you ask the question that we used to help the second patient, how do you activate MapKit-AP3? Medicannon or ChatGPT misses the answer, even though it was trained on the answer. And Medicannon GPT says, oh, let me look that up for you. Here it is right here. In closing, I want to circle back. I actually want to come back to Bertrand and finish out his story. So if you rewind to 2020, during the peak of the pandemic, his health slowly declined over the course of that year. He ended up, in fact, with multiple ICU stays. And, with COVID going around, I didn't know what or if might happen. So I decided on weekends to get him out into nature and take him on what I call a sunrise tour. So I started taking him down to the Gulf Coast or back to lakes up in North Georgia where I spent my childhood, just to get him out and experience as much of the world as we could, given the constraints of the time. And I'm glad I did. And I took his siblings here with him, of course, who loved it, going on the adventure. Because just a few days after this photo, with really no warning whatsoever, he actually passed away back in October of 2020. It was literally the shortest hospitalization of his entire life. All we know is it wasn't COVID. It was some other infection that converted very rapidly into septic shock. But, you know, I tell folks that I feel very privileged to have this job and to be the director of the Precision Medicine Institute, because what it means is that, you know, the work that he inspired me to do continues, and I get to continue to do it. You know, there's a lot of parents out there with children that have rare diseases, and many of their fates, if not all their fates in many cases, are very similar. But those parents don't have the ability to work for the legacy of their child as their day job. But I do have that. So I'm, you know, if you want to know more about his life, you can go to bertrand.mite.net and learn about it. There's actually an important document up there, which I'll talk about in a second, that someday might help somebody you know. If you want to see how we do this in real time, you can actually join our Zooms to watch case reviews Mondays at 11 Central. And again, talk to Alexandra. She'll get you the Zoom link for our next case review. But I want to finish by telling you what I've done each year since Bertrand passed. So for his 13th birthday, I actually wrote something called The Algorithm for Precision Medicine. This is up on his website. It's a 90-page guide for patients or patient advocates or caregivers that want to navigate the process starting from scratch. And it's what we do essentially when people reach out, is we walk them through this. And just a couple months ago, for what would have been his 16th birthday, I actually used that document to build a new AI, which I'm unveiling really for the first time publicly here today. It's a virtual precision analyst or an assistant for our analysts. And what it can do is it can step you through the process encoded in that document, representing 16 years of the knowledge I've acquired working in precision medicine. It is in some sense an AI that knows everything I know about precision medicine, thanks to Bertrand. So with that, it has truly been a pleasure. And one final announcement. So I don't know if you saw this. I got called to the White House last week, very, very suddenly, for a special announcement. And the announcement was that David Feigenbaum and I were getting a $48 million ARPA-H award. But the important thing is what it's doing, not the amount. The amount is just a necessary consequence of what we're trying to do. We have committed to using the AI I just described, Medicannon, to search for treatments for all 10,000 rare diseases systematically. And this is what it's going to take to do that. We'll be considering literally hundreds of millions of potential ways to treat all of these diseases in a comprehensive fashion. And so, you know, I couldn't help but feel like, in many ways, you know, this is a culmination. Well, it's not the culmination, but it's turning towards a culmination of everything I've been trying to do on behalf of patients to build this data set, and hopefully within 3 years have this available as a resource, telling us where the opportunities are to help patients right now and where they're going to be going forward. So with that, I appreciate your attention. Thank you, and I'm happy to answer any questions that you might have. So to answer the first question, so what we essentially did there is we kind of used human intuition, clinical intuition, to rank that tail. And the clinicians looked at it and they said, well, of the things on here, this is the easiest thing to try that also seems safe. They basically said, if it's going to work, it's going to work fast. And if it doesn't work, it's probably not going to do any harm. And so why not start there? So that wasn't AI making that call. That was humans looking at the results and saying, using our best clinical judgment, this seems like the most reasonable thing to try. To answer your next question, how often does it work? So I guess that you can break that down into two more questions. So first of all, how often does anything at all come back in terms of a recommendation? And then of those times, how often does something work? I'll have to appeal to Alexandra if I get this wrong. She's the one that actually runs the database and has a better sense of this than I do. But my sense is these days, I'd say there's about a 50-50 chance that something comes back as a possible hit. And my gut instinct says that, maybe 20% of the time, whatever that was actually seems to make a difference for the patients. That if you work it out, that number is both, astonishingly high and also far too low. Because it means that, the majority of the patients that are out there, we weren't able to help them immediately. Still, the fact that any meaningful fraction were immediately helped is actually really impressive because, remember, every single one of them was told there's nothing you can do. And then for some reasonable fraction of the time, we said, actually, there is something. And then for a good fraction of that time, it actually works. And what that's led to is a lot of patient stories over the years that we can now point to and say, look, this approach is real. For the patients where we don't get a hit immediately, we don't say, well, we're done. We say, well, it just means you need a different kind of science. It means that you might be building a model organism. You might be doing a drug screen. So it's not like if the AI fails, we stop. Which we just switch to a different kind of science at that point. Well, the good news is you shouldn't have to do anything, actually, because the way the program is structured is to systematically do it proactively for all known rare diseases. ASXL3 should be included in that list. And, if when you see the list come out, it's not on there, reach out to me and we'll make sure that it is. But we're trying to be as comprehensive as possible in collecting all rare diseases together to construct that database. I guess, in a certain metaphorical way, we're doing a kind of noise reduction in Medicannon GPT where, it's trying to actually check facts in real time. That's one way to think of, noise reduction, but at a very high level. If you look inside, the way neural networks are operating, in some sense, they intuit, certain noise reduction operations internally during the training process. I think the answer is yes in both senses. There's genuine signal processing happening, genuine filtering, genuine noise reduction. And then again, sort of, metaphorically at the high level, newer AI systems are learning to fact check themselves using more trusted knowledge sources in real time. Well, if they want to get involved, all they have to do is email us. And what we would do at that point is say, well, why don't you come watch case reviews? Come to a few Zooms and see if this seems like the kind of thing that you would enjoy doing. What they're going to see is their peers giving presentations on patient cases. Everything's de-identified, by the way, so anybody can join. But they're going to watch their undergraduate peers giving these genuinely incredible presentations. Like, they're astonishingly good to watch, where they've really dissected all of the information about this patient. They've then applied it to these tools. They've cross-checked everything in the literature. And at the end of a lot of these presentations, there's a list of recommendations saying, based on everything I've found, here's the things I think could help here, or here's what I think the next step is. And that's a lot of what the undergraduates do, is combing through the information coming in to assemble these very structured reports on the other side. To answer your question, yes. AI is capable of doing things like that, even in its present form. But I think we're entering a very interesting realm, because if personal injury attorneys can do that, clinicians can do it too. And I think the standard of care is actually about to shift. And I've heard this claim made repeatedly at this point, that it's a near future where not consulting AI will be malpractice. Because it can be so comprehensive in everything that it considers, in some sense, you're doing a disservice to the patient if you don't consult it for a second opinion. Now, ultimately, you can't I would never say you can just replace clinicians with AI. You need to have that human in the loop to make sure that what comes back from the AI is reasonable and actually still applies that all-important clinical judgment at the end of the day. My guess is, before we get to the point where, personal injury attorneys are using this to file lawsuits at scale, it'll probably be used in medical practice first to such a degree that that doesn't happen. So I guess there's several ways to look at this. Could an AI tool like this help draft an IRB protocol? Absolutely. Would you then have to edit it? Yes. but can it help you get a reasonable first draft? No question it can. Even better, it can criticize a draft, whether you wrote it or it wrote it, and say, hey, here are some issues I think you have with your protocol. Here are some things I think you should fix. And in fact, I think that, in fact, is sort of the killer application of this, whether it's IRB protocols or grant proposals, is AI is actually already much better at criticizing than it is at writing. Far, far better. It's same is true for humans, by the way. We're all better critics than writers. So it's no surprise the same is true with AI. And so the IRB can use it on the other side and say, can you analyze this and look for ways in which this protocol could be improved, or ways in which it violates the standards that we're trying to uphold. In the same way that AIs for radiology can sort of focus a radiologist's attention and say, you really need to look here, it can start doing the same thing for almost everything and say, I think this is where you want really close human scrutiny right now. I would say there's a future for this in accelerating both the drafting of, the editing of, and the review of IRB protocols. Absolutely. And more generally, I use these tools all the time for legal analysis. If somebody sends me a consulting agreement, I still read it. But the first thing I do is I say, I want this AI to read it first and tell me everything that potentially puts me at risk or in jeopardy from this contract or from this agreement. And it is crazy what it finds sometimes. It's like, did you know that the confidentiality period for this agreement is 20 years? I'm like, good grief, no. And so it has actually rapidly identified, onerous provisions and legal agreements that people are asking me to sign. And hopefully the old me would have caught those things anyway, because I like to read my agreements, but I catch them a lot faster using a tool like this. Yeah, so it's interesting, because you want to use AI to accelerate, but you don't want to ever fully fall back on it. We're entering a strange new world where in some cases you won't be able to tell the difference between a human doing it and an AI doing it. So the enforcement's going to get very murky very, very quickly. However, I do think part of the solution lies in the use of a diverse number of AIs to solve every problem. And so usually when I'm using AI in an automated way, I'm not using just one. I'm using 4 or 5 generative models all at the same time, even running each one several times over. You can have sort of a democratic process amongst a collection of AIs. And these kinds of uses of AI tend to give you much more thorough, much more comprehensive answers or analyses or reviews. And at some point, what we're going to have to do is do science on these things, like real serious studies to say, at what point are they so good that we trust them? In what ways do you have to use them so that you can trust them? Because their use is inevitable. And I think all we can do as scientists at this point is figure out how to use them responsibly and the guidelines for doing so. And it's an interesting question because it gets into the nature of how these things make their predictions and how they do what they do. And to a certain extent, their natural alignment is based on the frequency of what they see out there in the world. And the training data that they've been trained on, to the extent that they have a philosophy or a code of ethics, it's a weighted average of what they saw in their training data. That's what they get. The good news is you can do what's called a realignment of them, where you can actually, through a series of deliberately constructed conversations used as a second layer of training, you can give them a moral code. You can give them a sense of ethics that they intuit from the examples. Really, the answer to your question is they will have the sense of ethics and values that we give to them through that second level realignment. So it's really up to us at the end of the day to choose how we want them to behave. Why did he even feel the need to say it at all? Again, it all goes back to what they're trained on. So it is likely the case. It may have seen an image of a burger labeled with somebody thinking about it with anticipation, but even if it had never seen that, even if all it had seen was descriptions of Chick-fil-A sandwiches, and then other descriptions where people talk about how they enjoy eating Chick-fil-A sandwiches, it could have combined those together very fluidly and naturally during its training process to come up with the conclusion that whoever's looking at this sandwich is looking at it with anticipation. And again, because part of the way these things work is that what they're trying to do under the hood is predict the next most meaningful word in an interaction. That's why if you look at ChatGPT and it pops out word by word, it's just predicting one word at a time. To get really, really good at predicting the next word, it is unavoidable that you have to develop a theory of mind. You have to do it to get really good at predicting that next word, because the contents of the conversation could depend on the theory of mind and the contents itself. And so that's why they do it. And to get really good at predicting, it is just simply an inevitability that they will discover how to think about what people are thinking about.
Let's give Dr. Mike one.
Thank you.